In the following lecture, we're going to learn about ionic equations, and we will learn how to write ionic equations. Briefly describing what ionic equations are. In ionic equation is written in the form of dissociated ions in aqueous solution. And the other thing is that spectator ions are removed. Now, you probably don't understand any of the terms that I've used in these two in these two statements. So we're going to start from scratch, and we are going to learn how to actually figure out and write an ionic equation, and then you'll understand what these two statements actually mean. So I've listed over here some of the reactions that you've probably already studied. If you haven't studied these reactions, then it would be better that you watch the videos. That way where we learn to make these reactions and write equations and write balanced equations. So we studied all these reactions. There was a metal reacting with an acid, it would produce salt plus H2. Then you need to know this base and acid reaction that produces salt plus H2O. Then you have carbonate plus acid, produces salt, water, and carbon dioxide. Similarly, ammonium salts react with bases to produce salt, water, and NH3. And then there are some ionic precipitation reactions that are used to produce salts. And then there's an ammonia plus acid reaction, which is producing ammonium salt. Then there were plenty of redox equations and displacement reactions where a more reactive metal would displace a less reactive metal from its compounds, or it would apply to non-metals as well. For example, group 7, more reactive group 7 elements would displace less reactive group 7 elements from their compounds. So they were all redox equations as well. Now all these different reactions, or any reactions that you have so far studied, they can be written in the form, they can be converted into ionic equations. So we're going to learn how to convert any reaction, any of these class of reaction, or any reaction that you've studied so far, and we're going to learn how to write an ionic equation for that reaction. Now, in addition to knowing and writing equations and balancing equations, you must also need to know all about the solubility table. You need to know which compounds are soluble and which compounds are insoluble in aqueous state. So the first thing is that, and you probably already know this, all acids are soluble. So if you don't remember this right now, you can write this down, because this would be very important in writing, and this would be very useful in writing ionic equations. So all acids are soluble. So all acids are going to dissolve in water, and they're going to form an aqueous solution. Similarly, all group 1, NH4 plus 1 or NO3 minus 1 compounds. So any compound containing these three ions, they're going to be soluble. For example, NaCl is soluble, ammonium nitrate is soluble, calcium nitrate is soluble. Anything that contains nitrate or ammonium or group 1 substance, a group 1 cation, that's going to be soluble. The next statement is that all sulfates compounds are soluble. So any compound containing sulfate is soluble, but there are a few exceptions. Barium sulfate, except barium sulfate. So barium sulfate, SrSO4, PbSO4, and partially calcium sulfate as well, they are not soluble. Moving on, all carbonates and phosphates compounds are insoluble. So whenever you hear something carbonate, iron carbonate or tin carbonate or tin phosphate, anything that's phosphate or carbonate, that's probably going to be insoluble, except for if they already contain group 1, because we already studied that group 1 compounds are all soluble and NH4 plus 1 compounds are all soluble. So if it's a carbonate but it's a group 1 carbonate, then it would probably be soluble. So that's an exception. Then you have chlorides, bromides, and iodide. These compounds are all going to be soluble, and they also have exception if it's silver chloride or silver bromide or silver iodide, lead chloride, bromide, iodide, or mercury as well. So if these three ions are present, cations are present, then they would be insoluble. Then we move to bases. Metal oxides and metal hydroxides are bases. So they're all insoluble, mostly insoluble. Exceptions are again group 1 and NH4 plus 1, which we've already discussed. Anything that contains group 1 and NH4 plus 1, that's going to be soluble. So they're all going to be soluble. If it's a group 1, sodium hydroxide is going to be soluble because sodium is in group 1. And there are a few group 2 oxides and hydroxides which are also going to be soluble. Lower down in group 2, the solubility of oxides increases. So group 2, the strontium hydroxide, barium hydroxide are right at the bottom. So because they are right at the bottom, their solubility is much higher. They are very soluble. Calcium hydroxide is partially soluble. Magnesium hydroxide, which is right at the top of group 2, that's insoluble. So group 1 NH4 plus 1 oxides, hydroxides are soluble. And some hydroxides, oxides of group 2 are going to be soluble. And you should also note that whenever an oxide dissolves in water, if it's soluble, it no longer remains an oxide. Oxides generally change into hydroxides. So oxides and hydroxides are you can use them interchangeably. So whenever you have something, if you have sodium oxide and it's in aqueous state, then it's not going to remain sodium oxide. It's actually going to change into sodium hydroxide. So always remember this, that oxides, they change into hydroxides whenever they dissolve in water. Another thing that needs to be remembered is that if you have soluble acids, bases, or salts, so these are some of the class of compounds acids, bases, and salts that dissociate into aqueous ions. So when they dissolve in water, they break up into aqueous ions. They dissociate. What that means is, now to understand this, I've drawn this diagram. There's a beaker containing water molecules. These blue circles are all water molecules and they're moving around. And this is a tiny ionic crystal of a salt. Let's say this is NaCl, where you have a positive ion being attracted by a negative ion, which is then attracted to another positive ion, and so on. So this is this tiny crystal. And let's say this is NaCl and this is water. So what you're going to do is, when you try to dissolve, you put this crystal in water and you stir it. When you stir it, what happens is that this ionic lattice breaks. So by your vigorous stirring and the force that you're using while stirring, the negative ions, this ionic lattice scatters, it breaks up into positive and negative ions, and it goes and mixes with the water molecules present in liquid water. So in this other diagram that I've drawn now, by your vigorous stirring, this ionic lattice has scattered. All the ions, all the ionic bonds have been broken. The positive ions and the negative ions, they're all scattered and they're roaming around in this solution. And the reason they would not be able to form the ionic lattice back again, because you have plenty of water molecules. This positive ion would be attracting this negative ion, but there are plenty of water molecules that would come in the way. And so this positive ions and these negative ions, they would be attracting, but they would not be able to get back together again, and they're going to remain in this dissociated form. So this is your dissociated form. So one way to write this is, for example, this crystal was NaCl and it was solid, but when you dissolve it in water, when you dissolve it in aqueous, and it dissolves, NaCl is very soluble. All group 1 compounds are soluble. So initially it was NaCl solid, all the ions sticking together, attracting each other very strongly. But once you started that stirring, they all scattered and their bonds were broken and they're now dissociated. So the way to write an ionic compound in dissociated form is that now, since these ions are separate, so I'm not going to write them together, I'm going to write them in dissociated form. So Na+1 is in aqueous form, it's roaming separately, and Cl-1 is in aqueous form, and they're no longer together. So don't write them together like this. In solid state, NaCl was written together because they were all joined together, but in aqueous or dissociated state, they are now separate. So they have dissociated or they have ionized, and Na+1 and Cl-1 are now completely separate. This is roaming around freely in solution. This negative ion is also roaming around freely in solution, and they pretty much have very little chance of getting back together again. So this is what dissociated form is. And since I've mentioned that acids, bases, and salts all dissociate in aqueous state if they are soluble. If they're not soluble, then they're going to stay together. They're not going to dissociate. Only if they are able to dissolve in water, only then this would occur. So if some substance is not soluble, it's not going to dissolve in water, it's not going to dissociate in water. So you won't write this. You won't write them in dissociated form. Now this also not only applies to ionic compounds that dissociate. For example, acids are mostly covalent compounds. If you have HCl, now HCl is covalent, and it has a covalent bond, but when you dissolve HCl in water, acids also break up into ions, and H+1 and Cl-1 ions are formed by when the bond breaks, and the bond breaks unevenly, which is why ions are formed, and you get H+1 aqueous ions and you get Cl-1 aqueous ions roaming around in solution. So it applies to acids, bases, and salts. Whenever they dissolve in water, they dissociate into aqueous ions. So we're now going to learn how to write ions in dissociate form. So we've already done, for example, if you have NaOH, what you need to first know is how to identify which ions are present and whether the substance is soluble or not soluble. So if I have NaOH and I'm trying to dissolve NaOH in water, whether it's going to dissociate or whether it's not going to dissociate. Now NaOH is soluble or not, that is the first issue. So only if the substance is soluble will it dissociate. So we need to refer to the solubility table. So I've opened the solubility table, and if you look over here about hydroxides, NaOH is a hydroxide, it's sodium hydroxide. It was written that they're all insoluble except group 1 hydroxides. So which means that group 1 hydroxides are soluble. So NaOH would dissolve, it's soluble, all group 1 compounds are soluble, and it's going to dissociate. The other thing is you need to identify which ions are present. Now there's an OH minus 1 ion and there's an Na plus 1 ion. Na is a group 1, so group 1 has a charge of plus 1. So when you mix it, dissolve it in water, the ions would dissociate and they're going to separate into Na plus 1 and OH minus 1 ions. So this is how you're going to write NaOH when it's aqueous, when it is dissociated. The next example that I'm going to do is another compound, K3PO4, a potassium phosphate. Now I'm going to try and dissolve it in water. So how, if it dissolves in water, it's going to dissociate into ions. Now K again is a group 1 compound that we just studied, that group 1. All group 1 compounds are going to be soluble. So since all group 1 compounds are soluble, K3PO4 is going to be soluble. So it's going to dissociate into its ions. Now you need to identify which 2 ions are present. One is K. K is in group 1, it's plus 1. So K is plus 1, and the other one is PO4. The PO4 ion is the phosphate ion, which is PO4, and it has a charge of 3 minus. So it's going to dissociate into these 2 ions, but this compound over here has 3 potassium ions. So when they dissociate in this separate, you put a large 3. This big 3 over here means that now the small 3 in a compound means that they all join together, but when they dissociate, that means they all separate. So that indicates that all the 3 potassium ions are now roaming around freely in water. Phosphate ion is separate as well. So here is K3PO4 initially. This is the phosphate ion, PO4 3 minus, and all the 3 potassium ions are sticking to it. They join together and they're forming a compound, and then they dissociate. When you mix it in water, they dissolve in water. So that all the ions are dissociated. They're roaming around in water molecules. There are water molecules probably in between them. The phosphate ion is swimming around separately. The potassium ions are separate, which is why you write this big 3 over here. Now previously you had 3 potassium ions, but they were all joined together, which is why you wrote this small subscript 3. So when you're writing a compound, all of them joined together, you write the small 4 and small 3. But when they dissociate, so you have 3 separate potassium ions now, so you write this big 3 over here, 3 potassium ions in front of it, and there's only 1 phosphate ion. So this is how K3PO4 is going to dissociate and form 3 potassium ions and 1 PO4 3 minus ion. Let's do another example. This time I'm going to pick an acid, H2SO4, and we are going to dissolve it in water. Acids are all soluble according to our solubility table. So all acids are soluble. Now the first thing is that H2SO4 is soluble, so it's going to dissociate into its ions. Its ions are going to dissolve in water and they're going to roam around freely, separately from each other. So you need to identify which ions are present. There's an H plus 1 ion and there's a sulfate ion. Now H is going to be plus 1, H is always plus 1, and the other one is a sulfate ion. But now since it's dissociated, this molecule over here contained 2 hydrogen ions, and you wrote a small 2 because they were all joined together. But when you dissolve it in water, they're going to dissociate, like the example that I just showed. So the ions would be separate. There would still be 2 hydrogen ions, But you're going to write this big 2 over here. That means that they are now separate. They're not joined together. So it's going to dissociate. And in aqueous state, the 2 ions are going to be separately written now in dissociated form. The next example that I'm going to do is of aluminium carbonate. Aluminium carbonate is going to be aluminium ion and carbonate ion joined together, so it's going to be Al2. Aluminium is 3 plus, so there would be 3 carbonate ions in the formula. And if I try to dissolve it in water, aluminium carbonate, remember that aluminium carbonate is not soluble. You can refer to the solubility table. So I've opened the solubility table over here, and you can see carbonates. All carbonate compounds are insoluble except group 1 and NH4 plus 1, but aluminium is in group 3, so the first statement applies that all compounds, carbonate compounds, are going to be insoluble. So aluminium carbonate is not soluble. And what this basically means is that since it's not soluble, then it's not going to dissociate. So it's not dissociating, it's not dissolving in water. So the way to write aluminium carbonate is the 2 ions are still going to be sticking together. So you're going to write it exactly the same way. You're not going to dissociate aluminium carbonate. It would only dissociate if it was soluble. So since it's not soluble, it's not going to dissociate. Let's do another example of aluminium nitrate now. So aluminium nitrate is Al is 3 plus, nitrate is NO3 1 minus. So it's going to be aluminium nitrate. And if I try to dissolve it in water, now if you look at the solubility table, all nitrates are soluble. So anything that contains NO3 minus 1 is going to be soluble. So this compound over here is soluble, and it's going to dissociate into its ions, and there are 2 ions present in this compound. One is aluminium, and it has a charge of 3 plus because it's in group 3. The other one is NO3 minus 1. So it's also going to dissociate, and the 2 ions would be roaming separately in water. And since the 3 nitrate ions, there's a small 3, and initially they were all together, joined together in an ionic lattice, but once you dissolve them, they separate and they scatter. Now they're not together, so you write this big 3 now. There are 3 nitrate ions, but they are now separate. They're not joined together. So there would be 1 aluminium ion and 3 nitrate ions produced when an aluminium nitrate dissociates in aqueous solution. So these 2 ions would be produced in aqueous solution.